Today, we're diving into the fascinating world of intelligent agents and how they approach problem-solving in artificial intelligence. This module will guide us through the core concepts of AI, helping us understand how these agents navigate complex environments. Let's break down the fundamental components that make up any intelligent agent, its essential building blocks. At its core, an agent follows a simple cycle. It perceives its environment, processes information, and then acts accordingly. First, agents use sensors, which are like eyes and ears, to gather information about their surrounding environment. The control system is the brain interpreting sensor data and deciding what actions the agent should take next. Actuators are the agent's muscles, allowing it to perform physical or digital actions in its environment. The environment is the world where the agent operates, providing the context for its perceptions and actions. Finally, goals define what the agent is trying to achieve, guiding its decisions and actions towards specific objectives. Now, let's explore how agent architectures have evolved, becoming progressively more sophisticated over time. We'll trace this evolution, starting from basic reflex agents all the way to advanced learning agents. Starting with simple reflex agents, these are the most basic, reacting instantly to immediate situations. They react to current perceptions without memory, using simple if-then condition action rules for quick responses. Next, model-based reflex agents introduce an internal representation or model of the world. They maintain an internal state, updating it with new perceptions and understanding how the world changes over time. Goal-based agents are more complex, making decisions driven by specific objectives they want to achieve. They use goal information to decide actions, often requiring planning and search to achieve their desired objectives. Utility-based agents go a step further, aiming to maximize a utility function for optimal outcomes. These agents select actions that lead to the most desirable outcomes based on a defined utility function. Finally, learning agents are the most advanced, capable of improving their performance through experience. They adapt to changing environments, continuously updating their knowledge and improving their performance over time. Now, let's explore how intelligent agents navigate complex problem spaces to find solutions effectively. We'll compare two main approaches: uninformed search strategies versus informed search strategies. First, let's discuss uninformed search, which explores possibilities without specific knowledge about the problem. It systematically explores the problem space without relying on any specialized domain-specific knowledge. This approach uses only the information explicitly provided in the initial problem definition. Key examples include breadth-first search, or BFS, and depth-first search, often called DFS. However, uninformed search can become quite memory-intensive, especially for very large problem spaces. On the other hand, informed search strategies use additional knowledge to guide their exploration. They employ domain-specific knowledge, often called heuristics, to efficiently guide the search process. This allows them to focus on more promising paths, leading directly towards the desired goal. Examples include the asterisk search algorithm and the greedy best-first search algorithm. Informed search is generally more efficient, saving both time and computational space during problem solving. Let's delve into A*, a widely used algorithm in pathfinding and artificial intelligence. A* is known for its optimal pathfinding heuristic, ensuring efficient and best possible routes. The core of A* involves calculating the total estimated cost to reach the goal. This cost is represented by the formula f of n equals g of n plus h of n. Here, f of n is the total estimated cost from the start to the goal, passing through a specific node n. Then, g of n represents the actual cost incurred to travel from the starting node to node n. And h of n is our heuristic, the estimated cost from node n directly to the final goal. So, A* intelligently combines the actual path cost with a clever heuristic estimate. It guarantees finding the shortest path, provided its heuristic function is admissible and consistent. This makes A* indispensable for route optimization, game AI, and various pathfinding applications. Now, Let's explore constraint satisfaction problems, or CSP, a fundamental concept in AI. In CSP, variables, their domains, and defined constraints are crucial for problem definition. First, we have variables, which are the elements in our problem that need to be assigned specific values. These are the core components whose states we need to determine to solve the problem. Next, domains specify all the possible values that each of these variables can potentially take. Think of them as the set of choices available for each variable within the problem. Finally, constraints are the rules or restrictions on which combinations of values are allowable for our variables. These rules ensure that the assigned values are consistent and lead to a valid solution. Let's walk through a basic CSP backtracking process, a common method for solving these problems. This is a step-by-step approach to systematically find a solution by exploring different assignments. We begin by initiating the search for a solution, setting up our CSP problem. The next step involves selecting an unassigned variable to which we will attempt to assign a value. Then, we choose a value from the variable's domain and tentatively assign it to that variable. We check if this assignment satisfies all relevant constraints with previously assigned variables. If constraints are met, we then check if all variables have now been successfully assigned values. If a constraint is violated or no valid assignment can be made, we backtrack to the previous variable. This process continues until all variables are assigned values satisfying all constraints, meaning a solution is found. Let's explore some exciting AI applications currently making a significant impact across various sectors in India. AI is demonstrating its transformative power, bringing innovation and efficiency to diverse Indian industries. In urban planning, AI helps in optimizing city infrastructure, traffic management, and resource allocation for smarter cities. For disaster response, AI assists in predicting natural calamities, coordinating relief efforts, and managing resources effectively. AI plays a crucial role in game development, creating intelligent NPCs, adaptive difficulty, and realistic game environments. In e-commerce logistics, AI optimizes delivery routes, manages inventory, and personalizes customer experiences efficiently. All right, class, let's wrap up our discussion today with a quick summary of what we've learned. Here are the key takeaways from our lecture on intelligent agents and problem solving that you should definitely remember. First, remember that intelligent agents are systems designed to perceive their environment and take actions to achieve specific goals. We also saw that agent architectures vary widely, from basic reflex agents to highly sophisticated learning systems. Search algorithms are crucial for navigating problem spaces, and they are broadly categorized as either uninformed or informed methods. An optimal search efficiently finds the best path by considering both the actual cost and intelligent heuristic estimates. Constraint satisfaction problems define solutions by carefully considering variables, their possible domains, and the relationships between them. Finally, these core AI concepts are absolutely vital for developing intelligent systems used in countless real-world applications.